All right, another way to look at this variability, which we looked at it up here, right? So if a plot of the residuals, remember that's the difference between what my actual is versus what is predicted. So if a plot of the residuals against the explanatory variable shows a discernible pattern such as a curve, then the explanatory and response variables may not be linear related. Sometimes it looks like it could be a linear relationship, but the residual plot is that second level of defense, we'll say. It's the second level of defense saying, yes, it will be, no, it's not. So here's the deal. If there's no discernible pattern, like it's all over the place. So if my residuals are right here, this is just how varied it is. That's what it's talking about. This means linear is appropriate. See how this one kind of has a pattern? So linear is not appropriate because the residuals actually kind of have a pattern there. So you're going to see some residual plots in your homework, and then if there's no discernible pattern, it's all over the place, then that's how you know that. All right. And the residual, it's the same thing we figured out from that last section. Residual is just what's the difference between the two? How tight and how close is this data? Look at this one. You're going way up here for differences, way down here for differences. So if it's keeping it kind of a no pattern that you're looking at, but with a pattern, that's how you're out. All right. So a residual plot is literally that. It's that next level of defense to determine if it is a linear relationship or not. All right. The next thing we want to look at is this constant error variance. So again, with the variance here. This occurs if a plot of the residuals against the explanatory variable shows the spread of residuals increasing or decreasing as the explanatory increases. Then a strict requirement of the linear model is violated. All right, so if I am looking at this and it is increasing or decreasing, then increasing or decreasing, you got to see what I'm looking at here. As the explanatory variable increases, then a strict requirement of a linear model is violated. So then it's not a good linear model. That's kind of what we're saying is, oh, well, that's good to know, but it's not actually going to be a good linear model. Sometimes, again, it's that second level of defense. That's our residual. It's a second level of defense. You can look at this graph and be like, oh, wow, that's looking really good there. Yeah, that's set up. That's looking really good. But then as I'm looking at this, wow, look at as this increases, I'm getting more and more spread out, more and more spread out. That's what it's saying. So increasing the residuals increase or decrease, get farther away. That's what the residual is. Remember, that's the difference between actual and predicted. My residuals are getting bigger and bigger, meaning that the value of what I predict and what's actually happening are farther apart. Do you see how all this is relating? Okay, so this is that next level of defense here. So in this data, see how I'm starting to get some data values that are out here? That is what's happening here. Oh, it's getting farther and farther away from that regression line. My data is getting, let's write that out. Data is getting farther away from the regression line, right? So what I predict is going to happen is not necessarily what's going to be that prediction. That's what my residual is how accurate is my prediction from the actual data. And that's what we're pulling here. All right, that's the constant error variance. It's just what that's called. Okay, of that next level of defense. That's the moral of that story. We're just looking at what is that next level of defense. Good. And by that same token, we can look at these different graphs and determine an outlier. Remember, we've heard that word a couple of times already. So an outlier can also be thought of as an observation whose response variable is inconsistent with the overall pattern. So something that does not fit the bill, right? Does not fit what everything else is happening. The rest of these are all kind of lining up right here. This one is an outlier. All of this data is really close to the center of what we have. This is an outlier on your residual plot, right? The difference is beyond what we normally look at. A box plot. This outlier is outside of that fence, right? So all of that is happening. It's outside of that fence of what we're looking for, all right? So that is what you can see in several different ways in terms of having that outlier. All right. Another word for an outlier in this particular instance is an influential observation. That is going to be our outlier. An influential observation is an observation that significantly affects the least squares regression line's slope and or y-intercept. So it completely changes the line. I have a piece of data that's going to completely change my line of what I have. All right. Okay. So suppose that our golf ball experiment that we have already done here. So our golf ball experiment calls for 9 trials. Well, we've only done 8. But the player that we were using hurts his wrist. Luckily, Justin Thomas, a pro golfer, as you guys know, is practicing on the same range and graciously agrees to participate in our experiment. His club head speed is 120 miles per hour and he hits the golf ball 305 yards. Is Justin's shot an influential observation? So here is the least squares regression line prior to this new piece of data. So we now have a piece of data that is 120, 305. So that's our new piece of data. So let's put it in. I'm going to get rid of this. This is our new piece of data is 120 and 305. Now we're going to do the exact same thing. Stat, regression, simple linear. And I'm looking at my first column, my second column, and then we'll compute. So there's my slope and my y-intercept. My slope and my y-intercept, right? Okay, look at your correlation coefficient, right, that we're looking at. And we've got our slope and our y-intercept. So let's predict this. Let me get my, oh, I do already have it. Okay, so this is y hat is equal to 2.2287. We'll keep with the 4 decimal places. 2287x plus 2287 plus 39.4611, right? Okay. So we have this as my new least squares regression. So now look at what's happening here with my chart. Here was without Justin. This was my lineup of what I have for my least squares regression. Now Justin Thomas makes this hit. And that is my new linear regression line. Do you consider it to be influential? Yeah. Look at how it changes the line. It is considered influential if it doesn't line up, like if this dot had been right here, like if this had been Justin right here on this spot, then I wouldn't have to worry about it being influential because it's the exact same thing. Let me scoot this over a little since we don't need the stat crunch anymore. So right here, this is setting it up. If it had been right here, then it all would have been on the exact same line. The new one would have been the same. It would have been good. But that is not what's happening. Anytime it pulls that linear regression line, that is what's considered influential. It is that outlier. It does not line up with all the rest of my data. So yes, it is an influential observation. All right, it pulls a line, automatic influential observation. All right, we dove in, didn't we? That's cool, getting all this information about these linear regression lines. Well done, guys. Well done.